Hello. Today's video is a follow-up to the Shell theorem we discussed yesterday, which was about the gravitational force that a spherically symmetric body exerts on a particle outside of the sphere. Let's now consider a hollow ball. The Shell theorem says, in this situation, no net gravitational force is exerted by the shell on any object inside, regardless of the object's location within the shell. So today we're going to prove this part of the Shell theorem and discuss an interesting corollary of both parts of the Shell theorem. Once again, we'll use triple integrals, unlike Newton's original highly geometric approach. We'll use the spherical coordinate system once again, with r between r1 and r2, which are the inner and outer radius of the shell, and the two angle variables phi and theta are both in their default range. And without the loss of generality, we may place the particle m on the z-axis. And of course, its distance from the center of the shell, denoted as l, is less than or equal to r1, the inner radius. So the process of setting up the integral for the force is entirely identical to what we did yesterday, so it will not be repeated here. And this is the expression of the total force. We shall show that the inner integral in the blue box is 0. And surprise, surprise, the steps here are completely identical until a certain point. Just to recap, in part 1 we made this substitution, u equals to L squared plus R squared minus 2LR times cosine of phi. Applying the fundamental theorem of calculus, we reach this step. This is where the difference between part 1 and part 2 of the Shell theorem lies. This has to do with the sign of L minus R. In part 1, the particle is outside of the sphere, so L is always greater than R. But here in our situation, because L is less than or equal to R1, the inner radius, which is in turn less than or equal to R, L minus R is negative. And when we take the square root of L minus R squared, we get R minus L. And the rest of the steps are entirely straightforward again. And therefore F is 0. This proves the second part of the Shell theorem. And here's the interesting corollary. Suppose we have a spherically symmetric solid body with mass big M, and a narrow tunnel is drilled through the center of the body as shown. Further suppose that a particle with mass M may slide along the tunnel solely under the influence of gravitational forces. And the corollary says M undergoes simple harmonic motion. To see this, we denote the displacement of the particle m from the origin as x. Then we consider a concentric sphere with a radius of the magnitude of x. By part 2 of the Shell theorem, the portion of the body that is outside of the red sphere exerts no force on m. And by part 1 of the Shell theorem, the portion of the body inside the red sphere affects m gravitationally, as if all of its mass is concentrated at the center. Therefore, m experiences a force F pointing towards the center of the body, which has magnitude of g times m times the mass of the red solid body divided by x squared. The proportion of the red sphere's mass relative to the total mass is x over big R cubed times big M, where big R is the radius of the spherical body, which then simplifies to big G, big M, little m, divided by big R cubed times x. By the relation, big G times big M equals to little g times R squared, where little g is the acceleration due to gravity on the planet's surface. F can be written as g big R squared little m divided by big R cubed times x, which then simplifies to little m little g times x divided by r. So overall, F points towards the center of the body and has a magnitude that is proportional to the displacement. And this is exactly what characterizes the simple harmonic motion. Namely, the restoring force has a magnitude proportional to the displacement. Some simple calculation will give us the period of the simple harmonic motion. The equation of motion is given by the Newton's second law, which says mass times the acceleration is equal to negative mg over r times x. The negative sign indicates that the force is a restoring force. And we have a second-order linear differential equation, that is x double dot plus g over r times x equals to 0. And of course, g over r is a constant. And according to the theory of simple harmonic motion, this is the frequency squared. And therefore, the period t is just 2 pi over omega, which is 2 pi times the square root of r divided by g. Plugging in the radius g for the Earth, and we get that the period is about 1 hour and 24 minutes. Of course, this is a completely unrealistic model. Anything that passes through the center of the Earth will be burned to a crisp. That's it for today's video. Thank you very much for watching, and I'll see you next time.